Hello everyone, welcome to BPS the Atomic Explorer. I am BP Singh from the Physics Department at AMU Aligarh, India. Today we are diving into the fascinating world of Positron Emission Tomography, commonly known as PET scans. Get ready to uncover the intricate physics behind PET scans and discover how this remarkable technology bridges the gap between medical science and nuclear physics. Join us for an eye opening exploration that will change the way you think about the fields. A PET scan is a powerful imaging technique primarily used in medical diagnostics. It allows doctors to observe metabolic processes in the body by detecting pairs of gamma radiations emitted indirectly by a positron emitting radionuclei, commonly known as tracer. PET is basically a combination of marvels of nuclear physics, radiochemistry, engineering, advanced imaging techniques, and computational algorithms, which form backbone of these imaging techniques, enabling its powerful capabilities. The term tomography is derived from the Greek words tomos, meaning the slice or section, and graphia means describing or representation. As we look at this diagram of a PET scanner, let us identify the key components that make this advanced imaging technique possible. Here you can see the gantry, which is the large circular part of the machine. This gantry houses the detectors, which form a complete ring around the patient table. The patient lies on this table during the scan. The detectors are crucial as they detect the gamma radiations emitted from the tracer within patient's body. This setup allows for the precise imaging of metabolic processes, giving doctors a detailed view of what is happening inside the body. Stay tuned as we delve deeper into the science and technology behind PET scans, revealing how nuclear physics is revolutionizing medical diagnostics and treatment. Don't miss this exciting journey into the heart of modern medical imaging technique. Now let us dive into the physics of PET scans. At the heart of this incredible technology is the principle of annihilation radiation. Imagine this. A positron, the antimatter counterpart of an electron, meets an electron. When they collide, they annihilate each other, converting their mass into pure energy and producing two gamma photons that shoots off in opposite directions. This spectacular process is a direct consequence of Einstein's famous mass energy equivalence principle E equal to mc square. These two gamma photons travel in opposite directions to conserve the momentum. This annihilation process is fundamental to PET scans as it allows to detect these gamma photons and create detailed images of metabolic processes in the body. It's like watching nuclear physics in action right within the realm of medical diagnostics. The radiopharmaceuticals used in PET scans are typically isotopes such as using fluorine-18. The radionuclide fluorine-18 is typically produced in a cyclotron or in a linear accelerator by bombarding enriched oxygen-18 water with a proton beam. The fluorodeoxyglucose FDG administered to patients as a radiopharmaceutical compound is a glucose analog where a hydroxyl group is replaced by radioactive fluorine-18 atom. This FDG compound mimics glucose in the body and taken away by the tissues within the high metabolic activity. Such tumors and brain tissues which are highly having metabolic activity, they take up this FDG sample. This uptake is crucial for PET imaging, allowing the scanner to accurately detect the locations and intensities of radioactive emissions. Now, before the PET scan, a patient is usually instructed to drink a lot of water. This is to ensure adequate hydration and to facilitate the scanning process. Drinking water helps to fill the bladder, which can improve image clarity, especially for abdominal and pelvic scans. It also helps to flush out any residual FDG from the bladder, reducing background activity that could interfere with the scan results. Therefore, drinking water before a PET scan is a standard preparation step to optimize the imaging process. Once inside the body, fluorine-18 undergoes a nuclear decay process in which it transforms into oxygen-18. During this transformation, fluorine-18 emits a positron, which is a positively charged electron, and also emits an electron neutrino. This type of decay is known as positron emission or beta plus decay. With a half-life of approximately 110 minutes, fluorine-18 decays by positron emission in about 97% of the time and electron capture in 3% of the time, both resulting in stable oxygen-18. This half-life is ideal for PET scans, providing enough time to image metabolic processes while minimizing radiation exposure. Due to short half-life, coordinating the timings of production, processing, and transportation is crucial to ensure that fluorine-18 isotopes arrive at the PET scan centers in time for the scheduled procedure. Any delay in the transportation can result in significant decay of the radiopharmaceutical, rendering it ineffective. Now, when a gamma radiation is emitted, how it is emitted? So, when a positron encounters an electron within the tissue, they annihilate each other, producing two 511 kV gamma rays that travel in opposite directions. The gamma photons produced by annihilation are detected by a ring of scintillation detectors surrounding the patient. The detectors record the location and timing of gamma ray events. These detectors use materials like BGO, bismuth germanate, or LSO, lutetium oxyorthosilicate, which emit visible light when struck by gamma photons. This scintillation light is then converted into electrical signals by photomultiplier tubes or PMTs or silicon photomultipliers. In a typical PET machine, there are around 600 to 700 BGO detectors, and these detectors are arranged in the form of ring or panels around the patient, allowing for the detection of gamma rays emitted during positron annihilation events within the body. The exact number of the detectors can vary depending on the specific PET scanner model and manufacturer, but this range gives a general idea of the detector configuration commonly used in PET imaging systems. Now let us explore how PET scans work using this illustration. On the left side, we see a tissue slice with a hot spot where fluorine-18 accumulates. When fluorine-18 decays, it emits a positron, which quickly meets an electron, and this annihilation produces two gamma photons moving in opposite directions. On the right, we see that photons are detected by a ring of detectors. Each pair of detected photons form a line of response LOR, indicating where the annihilation process has occurred. So, by collecting data from multiple lines of response, the PET scanner constructs a detailed image of the tissue. This process helps doctors to visualize metabolic activity and diagnose medical conditions quite precisely or accurately. The gamma photons detected by the PET scanner are turned into detailed three-dimensional images using advanced computer programs and computer algorithms. These programs take all the information from the gamma rays and piece it together to show where the tracer has spread in the body. This process involves special methods like filtered back projection and iterative reconstruction method to create accurate images. So the final image show how active different tissues are, helping the doctor to see and understand conditions like cancer, heart disease, and brain disorders. The PET scans are invaluable in both medical diagnostics and research. They enable early detection of diseases, monitoring treatment progress, and conducting studies in neurology and cardiology. For example, in oncology, PET scans help identify cancerous tissues by highlighting areas with high glucose metabolism. Positron emission tomography plays a crucial role in monitoring and the effectiveness of the treatment in oncology. And the images you see here demonstrate the power of PET imaging in tracking cancer response to therapy. On the left side, we have a PET scan image taken before the treatment. The bright areas here highlight the red part and yellow part indicate high metabolic activity typically associated with cancerous cell. Notice the intense signal within the circled region which represents a tumor with high glucose intake. After undergoing treatment, the PET scan on the right side shown in the figure reveals a remarkable difference. The once bright and metabolic active tumor has significantly reduced in intensity as indicated by the much fainter signal within the surgical region. This suggests that the treatment has been effective in targeting and reducing the tumor's metabolic activity. The future of PET scan is bright with ongoing advancements in detector technology, image resolution, and new tracers. Developments in the time of flight, PET, and total body PET are pushing the boundaries of imaging capabilities, offering even greater precision and new applications in personalized medicine. The time of flight PET scanners are advanced medical imaging tools that use fast gamma ray detectors and sophisticated data processing. They measure the precise time it takes for the gamma rays from radioactive tracer to reach the detectors. This timing information creates clearer, more accurate images of the body's internal structures. The enhanced image quality improves lesion detection and allows for more accurate measurement of tracer uptake, and which is crucial for diagnosing and treating the cancer. Time-of-flight PET scanners also offer the advantage of faster imaging times, reducing the duration the patients need to stay inside the scanner machine. The image here illustrates how time-of-flight positron emission tomography scanners work. First, let us understand the key concept. In time-of-flight PET scanning, the precise location of annihilation event is registered by the detectors. The ring represents the array of detectors in a PET scanner that surrounds the patient. When an annihilation event happens, it produces two gamma photons, shown here as red stars, which travel in opposite directions. The detectors measure the time it takes for these photons to reach them. By calculating the time difference, they can pinpoint the exact location of the annihilation event inside the body. On the right side of the diagram, we see the point spread function or PSF. These functions describe how accurately we can locate the annihilation event. The solid black line represents an ideal situation with perfect resolution, while the red line shows a less precise signal as the distance increases. So why this is important? Time of flight PET scanners can measure these time differences very precisely, which significantly improves the accuracy and resolution of the images. This means better lesion detection and more precise measurements. And these are crucial for things like cancer diagnosis and treatments. Now let us explore the medical significance of PET scans with and without time of flight technology using the images shown here. On the left, we see a standard PET scan. This image shows the distribution of radioactive tracer in the body, highlighting the areas of metabolic activity. The intensity scale ranges from 0 to 4, but the image is less clear and blurred, making it harder to identify and locate lesions or abnormalities. This can be a limitation in clinical settings for diagnosing the evaluating conditions like cancer. On the right side, we have a PET scan with a time of flight technology. This advanced imaging provides a much clearer and sharper image. Here, the intensity scale is magnified to 100,000 times, indicating a higher sensitivity and more accurate measurement of tracer uptake. Medically, it means we can better identify and locate lesions or abnormalities within the body. The improved clarity and resolution are particularly beneficial in oncology for detecting small tumors, assessing their activity, and planning treatments. Now, comparing the two images, it is evident that time of flight PET scans offer significant advantages in medical diagnostics. The advanced image quality leads to more accurate diagnosis and assessment, making it an invaluable tool in medical imaging. Now, thank you for joining me on this journey through the physics of PET scans. By understanding the underlying principles, we can better appreciate the incredible capabilities of this technology in improving the human health. If you have any questions or comments, please leave them below. Don't forget to like, share, and subscribe to BPS, the Atomic Explorer, for more insights into the world of nuclear physics.